for joining. The topic today for the AI for Good session is continual learning in AI. So I think this is a very interesting topic, not fully resolved, but I just wanted to introduce the basics of continual learning. Um, so we'll go over like so what is continual learning? Foundations, challenges, some methods that people have tried, different scenarios, evaluation, continual learning in applied to large language models. Talk briefly about continual learning, continual reinforcement learning. So it's a combination of continual learning and reinforcement learning. Some applications on future directions for research. Uh, so why continual learning? So here, this is one example. We can imagine like many other examples. So you have medical diagnostic model, or like a healthcare model, that helps to diagnose disease for doctors. And the model must evolve with new disease, right? And the new disease appear, and they should be able to diagnose the new disease, but without forgetting the old ones, right? So also what we know that training these models is very often very expensive, too costly. So it takes a lot of time and sometimes impractical. So that's why there is that notion of a model that is able to learn on the go. Okay. Uh, so traditional like machine learning models or AI models, they often assume like IIDs, like static distribution, like they are identically distributed, independently and identically distributed for the regarding the data. Whereas like real deployment in the real world, the data are not often not IIDs. They're not stationary. They can change as change of regime. If it's applied to individuals, the individual behaviors can change. The environment can shift and so on. Right. So we want a model that is able to adapt and to learn. Um, for autonomous system, like IoT, Internet, IoT devices, so like mobile devices, um, self-driving cars, drones. Sometimes they have to operate without being connected to a server. They have been to be maybe they're like uh, far, or they have to be reliable even without access to a server. So they have to be able to learn too, right? So they have to be able to adapt without any connection to the cloud, right? So that's why you want a model that can continually learn. Um, so we know that these like AI models get retrained, but then they're trained very often because it's very expensive, right? Like a typical cost to train a model like AI model could be it's in hundreds of millions of dollars, right? To retrain at least. Uh, so. So retraining is not always practical and economically feasible. So you want the model to learn without being fully retrained, right? Another example for personalized devices, right? So you have AI like you have AI on your phone. Like let's say the next version of Siri will be probably more advanced, and you want Siri to be able to learn your behavior without necessarily forgetting all the past training that Siri had with Apple and with other users. Okay. So we know these slides come from that survey, but you have that of survey in on continual learning, but this is just a recent one. So um, so one core dilemma in the continual learning is what we call the stability-plasticity dilemma. Right? So this is very, very important. So stability means you talk about the AI model which is stable, that it retains past knowledge, right? All the training that it has received, it's not forgotten, right? When a new task comes, it doesn't like mess up all its past training. We preserve like a long-term memory of facts, of years, of of way of thinking. And the downside, if it is too stable, it doesn't evolve, it doesn't change. So they call it intransigence, right? So you refuse to learn new tasks, right? So so this is so you want a system that is stable, but you don't want what they call an intransigent system, a system that is unwilling to learn new things. Okay. So the trait of stability on one hand, on the other hand, you have plasticity, right? So it adapts to new information. So it's like more like plastic. It's like you can mold it or you can fold it. It generalizes across a task, on especially new task. Enables rapid learning, right? On the risk, is so good at learning new task, but then it forgets about the old task, right? It overrides the old knowledge, right? So this is the downside. Right? So plasticity to acquire new knowledge, stability to preserve the old knowledge. And one key risk that people emphasize in the literature is what they call what we call catastrophic forgetting, or CF. So the tendency of neural networks to abruptly and completely lose previously learned knowledge. It went down a moment ago. Okay, hold on. Microphone. Okay. Yeah. Volume. Okay, I try to speak louder. I think everything is all maximum already. Or maybe, okay, maybe I try this one. Maybe this one is better. Right. Okay. I hope it's better. So let's try with this one. Um, okay. So I'll try to speak louder too through the microphone. So catastrophic forgetting, the tendency of neural networks to abruptly and completely lose previously learned knowledge when it is trained on new information, right? So this is one of the central problem of continual learning. So here the example is that we train a network on task A, right? And those weights settle. So the weights in the neural networks settle in a given configuration so that you can execute task A. And so these weights are encoding what the network has learned. And then you train the same network, right, on a new task B, right? But somehow the gradient, so it's trained by gradient descent. And the gradient descent process adjusts the weights, right, to minimize the loss on the new task B, right? But in doing so, it overwrites the weight configurations that encode task A, right? Then suddenly the model cannot perform task A, right? This is what we call catastrophic forgetting. right? So if the neural network is very large, it's a bit less likely to happen, right? Because there's a lot of weight. So you could say that maybe in the like the very some of the new models have like trillions of parameters of weight. So this is less likely to happen. But it can still happen. Right? So it's still an issue. But for smaller models, it's more of a problem. Once you have like fewer weights, then it's more likely to hit like on the previous weights designed to execute another task. Okay. Uh, so these are like also example of problems of malfunctions, if you want. So the first example is what I just mentioned the previous page, the weight drift. So the weights are drifting, are moving. So the gradient updates to learn new task overwrites the weights of all the task, right? So the old knowledge is erased. You have activation drift, right? So the network's internal representation shift as new tasks are learned, right? So the inputs are processed differently throughout the layers, right? So then all the task is messed up. Different failure modes. So you have the called inter-task confusion, right? A model can no longer separate classes from different tasks, right? So categories that are like clearly distinct are suddenly merged, right? Intra-task confusion. So within the same task, right? So there's some features that we separate that once separated similar classes, I said a cat versus dog, become indistinguishable after further training, right? So it has the task. So let's say the task is to go to to identify a cat versus a dog, and then the new task is to identify let's say an elephant from a lion, and suddenly the features are processed differently, and a cat and a feature of a cat and feature of a dog are not very distinct. Task recency bias, where like the most recent learned tasks are favored, and the older tasks are becoming more and more irrelevant. Okay. A third category of malfunction is distributional shift, right? So the concept drift, meaning um, meaning that a given category has a different meaning. So here the examples like a car in the 19th century meant something pulled by a horse, right? A carriage, right? But today in the 20th or 21st century, a car means a motor car with an engine, right? So the same name, but the concept has differed. Domain drift, when the format or the inputs are changing, even though the labels stay the same, right? So here it's like digits, let's say 1, 2, 3, 4, 5, all the numbers. Initially, maybe the model was trained on handwritten digits, but now they're trained on printed digits, right? So the same categories, but the visual appearance might differ, and then the model could get confused. Okay. Uh, There are like different like types of continual learning, and you see a graph. So from the same survey. So what you have first the task and incremental learning. So the incremental learning, so you have new data, new task to learn, a different way to learn it. So class incremental learning means the task identity is known at training and test time, right? So here you see in the graph, the task is identify a dog versus a duck, right? Or an apple versus a cherry, right? So it'd be the task N, task N, right? So at training time on test time, the task ID is known, right? So how the work is a bit easier, right? This is the easiest like scenario for continual learning. Class incremental learning is at test time. Uh, we uh, we don't know. At training time, we know the task ID, By test time, we don't know. Right? So at test time, the model has two features to recognize what task it has to solve. Okay. And then the third one, domain incremental learning, is that we don't know the task neither in training time or test time, right? So this is harder. So the model has to not only identify what task to solve, but also retrieve its memory or its neural network what model to apply, right? So somehow could say like large language models are more in the domain incremental learning, right? There's no task ID when you ask, you do a prompt, you don't say this is a task that you have to solve. It will infer the task, by your questions, of course. Okay. Uh, so going to over like not too much in details because it's quite long, but on these surveys, like they explain this pretty well. So like five analyses of solutions to address these failures and to implement continual learning. So we have the regularization, replay, representation, optimization, and architecture. Right? In fact, new solutions, hybrid solutions now, they combine some of these solutions together. Could be regularization with replay with representation, et cetera, et cetera. So and then it's an empirical question. Is it which one is the most effective, but it's also the less costly and take less time and resources and so on. So we see also the cost and benefits of these different approaches. Okay, first regularization-based method. Uh, so we talk about like a weight drift, right? So the weights are changing too much, then it will mess up the performance of some previously learned task, right? So what people do is what they call weight is regularization, right? Usually regularization in machine learning is a way to first you fit the model. Regularization is a way for the models not to deviate too much from the previous version. That's what we call regularization. Or sometimes you can that you want to be very conservative, so you want to assume that the weights are close to zero, and then there's a regularization term to force the weights to be very small. Right? It's just another way to do regularization. Right? So there are different ways to do it. Uh, so sometimes it will be to weight. They will estimate which weights are like the most important, for instance, for previous tasks, and try to change these weights to not either not to touch them or to touch them very very little, right? So there will be like penalty for like a higher penalty for important weights and fewer penalty for smaller weights. So when recalibrate when the model learns, it's not going to change the important weights, but change only the less important weights. And very often it will appear in the objective function. So these are the different solutions. I'm not going to go into detail. All the details, but usually there's an objective separate for weight or weight deviation. Okay. Another way to do it is a kind of regularization too. That's why it's here. Is what they call knowledge distillation. So knowledge distillation is to learn from an old model, often it's in fact learning from a bigger model, but he'll be learning from an old model to teach a new model, right? So it's having a teacher and training the student, right? So the new model becomes a student of the teacher, right? Because the teacher stays the same, so we hope that what the student learn doesn't deviate too much from what the teacher is teaching the student. And there's like different levels of what the teacher is teaching the students, right? So it could be features or the activation or different terms. So it depends on what knowledge is distilled from the teacher, right? And because the knowledge comes from the teacher, it is untouched. So the new model, when it's learning new task, there's a hope that the model is going to, it's not going to, the model is still going to remember what it has learned from the teacher, right? Um, so there's strengths and limitation to regularization methods. Is that it like memory efficient, right? No new data are stored. It's only the weights, right, of the model. It's privacy friendly because we don't see the data. It integrate to in existing pipeline, right? And it works across the different like continual learning configure settings. The limitations, the estimations, simply such as the realization estimation can be expensive, right? It can degrade along long sequences of new facts or new tasks, right? There's a risk of the weights being too not changing that much, so what they call the risk of intransigence. And learning new tasks becomes difficult because the penalty of let's say we don't want the weights to change, and learning new tasks will be impossible, right? On some, so there's a problem of scaling on being too conservative. Regarding knowledge distillation, there's a risk of domain that is sensitive to domain shift, right? The domain is shifting because the teacher model is still the same, right? So the student might be ill-equipped, right, to address the new domain. Okay. Replay methods. So replay methods is so this is typically done. For instance, you must have seen it for AlphaGo or AlphaZero. So replay is like you generate new data. For instance, AlphaGo it says the AI replay against itself. So here, it's the replay is to have a memory buffer of past examples, right? So the fear is to forget new old task, right? And the way to remember new old task is to remember past examples, right, of models to follow, right? So you have a memory buffer of past examples that can replay, right? It's like rereading a book that you have read like a long time ago. So you reread the book or you read like chapters of your old book so that it's fresh in your memory and you don't forget the old books, right? So there are two ways to do it. Either you just use the past examples or use the generative models that can generate pseudo examples that look like past examples, right? So this is what you have on the left, on the right, generative pseudo replay. So it's not so replay something that looks very similar to the old books that you have read in the past, but then that's exactly the same, but they have the same flavor, right? And then you mix it with the new task, right? So by doing that, so the way then when you learn, you don't forget, you don't have that catastrophic forgetting, right? So the strengths, it works pretty well empirically. You can mitigate class imbalance, so because you can generate the data as many as you want. Limitations, it requires a memory buffer, right? There's a risk of privacy if the raw data are used. So it is like a healthcare system where you have, the disease, the symptoms, and so on. And you might sometimes identify the patient, so it could be a risk. Or even like if you have a few examples and you see how the weights are changing, maybe it might be possible to reverse engineer the model and identify the raw data. Okay. This is replay. Okay, representation methods. So, so the advantage of so learned representations are more stable and transferable. A representation that you simplify is a bit like PCA, principal component analysis. So you have an object, or like, and then you summarize that object with some characteristics. Right? It's like it's a representation, right? So. Uh, so either you can we leverage the representations, or in fact what we do, we leverage the pre-trained model, right? And we don't change the sorry. Um So we don't change the model, right? But we add we fine tune the model using like technologies so that such as like what we have like LoRa, so the to to learn, right? To learn on new data, on new tasks without changing the master model, right? So because the pre-trained model is very expensive to train, so you don't change any weight, but just add a small like a module, right? To learn new tasks, right? So this is very popular, and this is used a lot, as you can search the literature. And this is in the category of what we call PEFT, parameter efficient fine tuning. So you fine tune the model using like models such as LoRa. So it's almost like a kind of it was like a linear regression on the new data, and this is typically based on like I think there's a slide. I may go a bit more in details on like very simplified matrices, low dimension matrices that you train right on new data, and it's very cheap to much cheaper to train that. Okay. Uh, so the limitation, so the limitation is that you need a very good, like a large pre-trained model, right, to do that. And maybe if you have also too many tasks, these adapters saturate, right? So they might be able to learn many new tasks, right? So this use a lot for vision. Vision model. But this looks promising. Okay, optimization methods. So this is so before we talk about the weights. Uh, this we talked about the weights. So here is to intervene directly during optimizations. Where so before the weights are changed, so we try to intervene by changing we constrain the gradients. Right. So we know that all these things are calculated by gradient descent. Gradients are like the first order derivatives, right, of the objective function. And so you constrain the direction of the gradient so that learning new tasks doesn't increase the loss of the previous ones, right? So there are like different techniques, gradient projection, null space operations, or meta learning. So just to give you a flavor of the gradient projections, so you know the direction of the gradient, right, for to calculate new weights, but then you make sure that it doesn't interfere with the gradients of the other weights, right? For the other task, right? For the other task, you know the gradients, or you make them orthogonal, right? So the new gradients are changing, but they don't affect the previous weights, right? So it's another way to do that. So you make sure that the weights for the previous task are not affected, right? Null space is a way to project the gradients to a space orthogonal to the gradients of the previous weight, and you optimize only that in that space. Okay. Meta learning. So it's a topic in itself is to learning to learn, right? So these are like models where you learn so the model is trained to learn new tasks, right? And because it is part of the objective functions, somehow we hope that it work better, right? We learn. So let's say in sample, like in the testing data is trained on like separate task, and testing is trained on new task, and then if the model performs well, so different techniques to do that. It's a model that should be robust to continual learning. Okay. A weakness of meta learning here I mentioned here is if the data the distribution shift, the model might break down, right? So it's not it's still a bit theoretical. It might be, but we definitely want something like this for in robotics, right? Robotics, if you cannot train the robot to do everything, and not everything can be in the data, right? But to learn somehow to meta learn, meta teach maybe the robot so that even in different slightly different configuration, it be able to perform. Okay. So we are almost done with the different methods to do continual learning. So this one is what we call architecture methods. So it means that the architecture itself is changing. So how we optimize, what model we optimize. So it's not so we don't optimize the same model each time. And one example I'll give you is when we use a mask, right? So we mask. So we know the previous task, we know which weights are important for this old task, and what we do, we mask this weight, right? And for the new optimizations, we don't allow the new the new learning to affect these old weights because they are masked, right? They're not seen. Okay, so and then there are different variation. So you see that the new model that we optimize is a different model, right? Because there'll be a lot of weights will be masked are not visible. So in fact, it's a different networks that we optimize. That's why it's called architecture. So fixed capacity versus capacity increasing method. Fixed capacity means that the weights are the same. So some are masked, some are not masked. And capacity increasing means that we can add new layers, right? So limitation is that, especially for the capacity increasing methods, that the more tasks you have, the bigger the model has to be. Then it might not be feasible to increase, the model indefinitely. And if the model is fixed, a fixed capacity, then we might exhaust all the weights, right? So if it's again, like, infinite number of tasks, and you have a situation where maybe all the weights are masked, then there's nothing to optimize, right? Kind of extreme. Extreme situation. Also, when we add like new layers, new networks, what they call module networks, there'll be there may be too many module networks to route the model. Let's say add the task and route it to the particular networks. It might become infeasible to do. Right? So how do we evaluate this all these techniques, right? So you can look at the accuracy of the model. Uh, you can see like how the accuracy is changing when you train on new task, and how the incremental accuracy, how does it differ? So you can focus on the old task, after training on new task, if the accuracy on the old task has changed or not, and look at the dynamic. Uh, so you have also like memory stability. So there's a forgetting. So say like, what's the performance of the earlier task. There's something, a notion interesting, it's like backward transfer. So is learning a new task, does it positively or negatively affect all the tasks? It's called a backward transfer. So forward transfer is all tasks to new task. Backward transfer is from new task to old task. Learning plasticity, right? So there's a measure of intransigence. Do the weights change? That does task. Does it improve? Is accuracy on new task increasing or not before after training? If after training accuracy has improved, it means that the model is too intransigent. It's unwilling to learn new tasks. Right? Then I mentioned forward transfer. So these are different measures that people use. So ALC, area under the learning curve. So it'll be a matrix, let's say, of loss minimization versus training time, right? So you can see, is that curve going down? Does it go down fast enough? Time to adapt. How much time does it need to adapt to new tasks, to have a decent performance on new tasks? Because if the time to adapt is infinite, it means the model is very intransigent. Budget. So this is like if you have like some budget cost to training the model versus retention of the model of the old task. DP, I think it's differential privacy. budget. So if you have like in healthcare, you worry about the privacy of data, so you better have a budget for that. Right? Okay. So for large language models, in fact, the ones that we use, like every day, like ChatGPT and etc., they're large language model. Uh, they are the continual learning is applied at the three different stages, right? So there's a pre-train at the pre-training, right? Instruction tuning stage and alignment stage, right? So pre-train is the when they do like full a full run, right, of the model. Instructioning instruction tunes like when did you train the model to answer the questions of the users correctly, right? So usually that it has to be instruction tuned so that the questions are answered correctly. It's not just like pattern recognition and autocomplete. Okay, on alignment. So alignment, so that it respects, it doesn't it stays polite, he tries to be truthful, he doesn't mislead, or he doesn't give the dangerous instruction, etc. And it learns to refuse to answer when the questions are too are not proper. Okay, so the continual learning can happen in these three stages. So there's a survey that you can consult. Uh, um, so there's first here I'll mention continual pre-training, even though that state is less uh, is somehow is used maybe probably between run, but these models are not trained like very frequently, right? Because of the cost, right? Even though these days it seems like a new model comes out every month, so maybe once a month, maybe they do a full pre-training, or once a quarter they will like fully retrain the model or and enhance the model, right? So so it's necessary because you want the model to be trained on dynamic data stream, right? You say like who is the president? You ask the model who is the president today. You don't want the model to say Joe Biden, right? Or Barack Obama, right? The model has to be able to have seen the most recent data. And so you want to absorb all the factual knowledge. So you want to know you want the model to know who's the new president today, but you still want the model to know who was the president, who was the first president of the United States, right? So you don't want the model to forget that. So there's different ways, two approaches to update knowledge. So domain incremental, like a pre-training, or domain-specific training, right? So you accumulate knowledge across multiple domains, or you specialize, you turn the model into a specialist for particular domain, finance, healthcare, and so on, right? Um, So continual instruction tuning, instruction tune to apply continual learning to instruction tune model. So continuous fine tuning on new task instruction, right? So it is a measure risk. So we use techniques like LoRA, right, that we've seen before on particular subspace, prompting, or what you call retrieval-based adapters, right? We also learn that we can also have you can also teach the model to learn tools, right? Like a search engine. So now you use right now you use ChatGPT, Gemini, Claude, and so on. They can use search engines, calculators, APIs, and so on. So for instance, even though the model has been trained only, let's say, a while back, you can use search engine and you say, okay, who's the current president of the United States? You can use a search engine, access Wikipedia, and see who's the latest president. right? So this so different ways to address catastrophic forgetting on continual learning. And then the last part is continual alignment, right? So you want the model to continuously reflect ethical guidelines, regulation, social norms, on the things that people find out and they want to correct. And you don't want to wait for the next update for the model to learn this, right? So the new preferences, of course, you deploy the model to another region of the world where the laws and regulations are different. So you want the model to be aligned to the local regulation. Okay. Uh, so this, yes. So this is like to spend a bit more time because this is quite important. So these efficient parameters, efficient fine tuning, right? Uh, so like a large model costs like millions of dollars, and now even like hundreds of millions of dollars. Uh, these PFT techniques, they change only like a very small fraction of the parameters, so they're much cheaper, right? So so instead of updating hundreds of a trillion parameters, it will update maybe 1 million parameters. Right? So this is much cheaper, and because it's not the backbone model, the large language models itself is not touched, right? The 1 trillion parameters are not touched, so all knowledge survives, right? Because there was no interference, right? So I just talk about first the LoRa. So LoRa LoRa has been around for a year or more already, right? But it's a low rank adaptation. So it injects a small trainable low rank matrix alongside the frozen weights and matrices. So only the wrong decomposition matrix, right, are updated, and the backbone never change, right? And you have like a big family of LoRa. LoRa could be a topic of a talk in itself. So the only like small matrices are changed, so so it's very cheap to update, right? Uh, a way to do it is also to do it in the prompt, right? Add some predefined prompt to the prompt that the user is giving, right? So to learn new facts. Uh, and then uh, and then we have modules that you can add. So this is what they call like bottleneck modules, feed-forward modules, right, inside each transformer layers. And then the adapter are trained. So it's kind of same spirit as LoRa. Okay. So continual learning, um, continuous learning of this pretrained knowledge of the entry strap. So yeah, so this PEFT uh, solve the problem of not interfering with the old task, catastrophic forgetting, because it doesn't mess up with the old model, right? But the second task, it does well for some tasks, but it's not infinite. So usually people combine PFT with replay or regularization, what methods that we have seen before. Okay? Yeah. CF is catastrophic forgetting. Right? It's catastrophic forgetting. Uh, okay. So here I talk briefly about continual reinforcement learning. So continual reinforcement learning. So it's um, so large language models just learn on internet data, on on books, images, videos, and so on, YouTube videos, etc. Right? Reinforcement learning is more applicable to robotics, where you have like an AI that evolves around the environment, right, and performs some actions and learns from its actions because its actions triggers a reward, positive or negative, right? And so this is the reinforcement learning loop. So it can be like, I mean, reinforcement learning is used for games too, right? But it's ideally we would like to play to robotics. But of course, so in the time of person in robotics, you want the robots to learn, but also to continually learn, right? So let's say we send the robots to Mars, right? You might not have internet access in Mars or not having like internet access all the time, but still be able to learn new facts, new tasks on the go while it's very far from planet Earth, right? And then if we let's say we colonize Mars with like robots, so these robots should be able to learn new things without being especially trained by us back on Earth. So this is very important. So that's why continual reinforcement learning is very important. So it's so adapt to we want like a robot to adapt to new task, arriving sequentially without restarting from scratch. So we don't want to retrain all the work and all the facts and retain knowledge, right? So the robot on Mars, it will learn new tasks to perform on Mars, but you don't want the robot to forget everything it has learned on Earth. Okay. So that's why continuous learning and catastrophic forgetting is still very important. And for transfer, so we hope that anything that it has learned on simulation on Earth or from Earth can be applied to Mars, right? So astronauts are like that, right? We have simulation on Earth, and we hope that what they have learned on Earth, on the moon, maybe at one point we'll have we have astronauts permanently on Moon. Whatever on Moon could be transferable to Mars, even though Mars and the Moon are very different. Okay, so we have these, especially in continual reinforcement learning, the triangular like trilemma about balance. So stability, right? We've seen that. Plasticity, we have seen that. And scalability, right? So learning new task, right? So learning new task within compute and budget. So we can have like a network that grows infinitely with all the tasks. This is very expensive, etc. Right? And so this continual reinforcement learning, and this has been, I think, very important topic for the years to come. Uh, okay. Okay, so this is also something, also an important concept. Uh, it's what they call continual compositionality. Okay. So this is a concept that says that we want to move from a monolithic model like a super like big like neural networks to a dynamic decentralized ecosystem of AI models, right? And so we cannot just rely on just a super AI, but a family of AI and maybe like specialized AIs, right? So continual compositionality, so scalable, modular approach to intelligence, but multiple specialized foundation models, right? And agents are dynamically orchestrated, right? So if I go back to the example on a colony on Mars, so you have robots, but maybe all the robots don't need to be the same, right? It doesn't have to be like super like ChatGPT and so on, but they could be like a specialized robot models, robot for healthcare, robot for construction, robot for driving, robot for exploring planets, etc. Right? So like a human society where we are all relatively specialized, right? You have construction workers, you have doctors, nurses, etc. Right? But then we need so all these AIs. So they can be composed. So you can compose a team, right? We say like, okay, we send robots on Mars. What kind of skill sets we require? So it will be composed. It could be well combined depending on the mission. A different set of AIs working together. But also we want these teams to be flexible in case of emergency to be able to adapt and relearn their skills, right? Even though let's say we send a robot doctor on planet Mars, and somehow we discovered there's like Martian there, or like some Martian animals or whatever, like a bacteria. Then the robot doctor should be able to adapt to either cure like Martian disease, or to cure to treat like Martian species, bacteria, etc. Right? So this is a very important idea. So we don't see that too much today, but I think it will come. Like AIs are going to be more specialized, and we have the ability to make them work together on the top. I give you the here you have the source of this interesting paper. Okay. So the application are obvious, right? So you need like a model that can learn for computer vision to recognize new objects. So let's say we go on the robot on Mars, it will see things that it has never seen before, but still be able to function, right? Healthcare for the same thing. You have new data, new input data, new techniques maybe to scan the body, etc. New resolution, maybe higher resolution images. So that you have run like models to work also to work with new inputs. Autonomous system. So this is well known, like say drones. So drones, if they are sent very far, they should be able to, we want them to be able to learn, right? To learn on the spot. Otherwise, we will send them very far, and the weather is changing, right? It's become darker, it's snowing, or it's raining. So even though you might not have seen the exact configuration, we want the drone to learn that, or let's say like a learn for defense application. So the drone gets shot, right? So it shouldn't be specific to the ammunition used against the drone, right? So if it's shot, it should be able to learn to adapt on the caliber and the ammunition and so on to be able to learn on the spot and defend itself. Okay. Cybersecurity, it's obvious too that malware is hackers use new tools every day, right? So should be able to adapt on the spot and to detect new attack signatures without being retrained from scratch. Okay. I mean to skip that, but you can find it in a survey. Um, I just mentioned so future research. So this is like a very big area of research. The last topic, how do we regulate audit a model that continuously learn, right? So the model in fact can be changing day every day or minute after minute, right? So you might approve a model for release, right? Let's say in Europe some big models have to be approved. So but then the model is learning all the time. So what tells you that this model 1 month from now is the same as the first one, right? Or then you might need to have a continuous audit of models, right? On maybe on detect when the new model is deviating so much from the original model, triggers like new governance rules on so on. Okay. But a lot of it is also continuous learning is also economic cost. Right? The cost is still expensive to continuous learn. So how do you do it efficiently? So key takeaways. So we talk about catastrophic forgetting. Right? So something so you want to learn new things without forgetting the old task. Not single methods dominates. Why we talk about regularization, replay, representation, and so on. We often have a hybrid approach, right? Or we talk about PEFT, right? The prioritized efficient fine tuning. So this has been to be maybe combined with replay, regularization, right, to work well. LoRa we talk about LoRa a lot because it's used today. It's used today a lot. Evaluation. So evaluation can always be pre, be improved, and we talk about some of these example area, another learning curve, retention at the budget, right? So continual learning is still a very important topic. So in LinkedIn, as I said, like, if I were to do a PhD today on I think it'd be very interesting to do to do some research in this in continual learning. Okay. Okay. So this time I'm going to stop here. If you have any questions, please raise your hand and I'll let you. We can take a couple of questions if you have any.